of the academic year and the first talk of the year 2021 in the Science Sabha series conducted by the Physics Club NIT Surat. This is that one talk which intends to question the foundations and philosophy of physics and try to make sense of our reality. I request Ramkumar to introduce the speaker to us all.
So, good evening, everyone. So, it's a great privilege for me to introduce Dr. Abhishek Majhi to you. So, Dr. Abhishek has done his master's in physics from IIT Kharagpur, and moving on, he did his PhD from Saha Institute of Nuclear Physics at Kolkata. After his PhD, he did a couple of postdocs, one at Institute of Mathematical Sciences, Chennai, and another one at UNAM, Mexico. So after his postdocs, currently he is right now he's working as an Inspire faculty at Physics and Applied Mathematics Unit, ISI Kolkata. So it's an immense pleasure for us to invite you, sir, for the talk.
Okay. Thank you, Ramkumar, for this kind introduction. But I would have liked to have this introduction after the talk because you have already told me that I have done my PhD and postdocs and etc. And in the poster there was written like Dr. Abhishek Majhi. But from the title of the talk, you all can understand that I will be talking about a few things today in physics, which is actually related to some of our childhood questions, irrespective of whether you were a brilliant student or a backbencher like me. So, whenever you feel uncomfortable with whatever I talk today uh, during this seminar, please ask to me in a scholarly fashion and not just considering yourself as a student and myself as some faculty or something else. Okay. So I have removed the doctor from the slide. You can see. So my name is Abhishek Majhi and that's it. Okay. So there are two broad aims of this talk. Of course, to raise some reasonable doubts regarding the way physics is done and to attempt to unsettle a few minds, at least one among those who will be listening to this talk. So there are two declarations here. You will be requiring no knowledge beyond college level physics throughout this talk. And of course, some discomfort may arise regarding the knowledge of school level physics, whatever you have learned. Sorry. Okay, so this talk is basically based on a very recent paper of mine, a logico-linguistic inquiry into the foundations of physics, part 1. And this is the title of my talk also. And this is only available on ResearchGate because my papers are now barred from being posted on the archive for maybe valid reasons that I don't know. Okay, so here is an outline. Okay, so what is this talk going to be? Many of us actually think that science is very logical and the most reasonable way to look at whatever we observe and explain. So from this perspective, I am going to begin with a few questions, very basic ones, which you have learned in your schools, class 7, 8, or 9, 10. And while bringing out those questions, I will put some questions from the logician's perspective and point out that the logicians don't ask those very basic questions which should have been asked. So that is the more or less the first topic. Then I'll go into explaining that what I'll be meaning by definition, the word definition in this talk, because you will see often the physicists use those words that, oh, let us define this thing, let us define that thing. So what do we mean by definition? Then I'll go on to discussing some elementary things which you all know. There is nothing new here. And this quantity, physical dimension, and number. And then there will be something new which will come up, which not in physics but from the logical perspective. The physical dimension and the middle way. What I mean by the middle way, I will tell you. Then I will clarify the words unit and unity, which also you know. And finally, after having these discussions, I will enter the definition of the electric field, which you study, I think, in class 12 and then also in college. Then I'll proceed towards the conclusion by providing some comments on Maxwell's definitions and my comments on Jackson's definitions. Jackson is J.D. Jackson, you know, there is a book which is mostly studied in the bachelor's and sometimes in the master's. But don't worry, I'll stick to only the definition of electric field. Then I'll show that there is a necessary postulate that is missing, which we need to define what is electric field. And then I'll conclude with some remarks, which will be also both new and not new. So you all know this. I'll tell you what. So let me go into the first thing, the physicist expressions and what do I mean by the logician silence. Okay, so this you all know about physical dimensions. That is the distinction between physics and mathematics. In mathematics, you don't have that. Time, mass, space, and those sort of things. You only work with numbers and etc. So what we do in physics is that we express the thought of physicality with these sort of verbal expressions, mass, length, and time. And we use the abbreviated symbols, MLT. Here in the second bracket, you can see. So these are required to make the distinction between the number and quantity. And if we replace the words like mass, length, time, etc. by numbers, then we will not be able to communicate. Like if you go to the shopkeeper and say that give me one rice, there is no meaning of that. You have to say that, okay, so 1 kg and these sort of things. So here comes the units then. So these are the verbal expressions like kilogram, meter, second, corresponding to mass, length, time, etc. And these are the abbreviated symbols we use. Those are also not numbers, these units. And these are the conventional chosen standard quantities with which we measure other things in multiples, that is whole numbers. And this was also clarified by Einstein here in one of his book about special relativity and general theory. Okay, so there are two basic lessons here we have learned. So in arithmetic, we learn that we do addition, multiplication, etc. With numbers, and then in physics we have these physical dimensions and units are not numbers, as we have seen, and you all know. So what are the meaning of these expressions then? You all do dimensional analysis. So for example, this fourth dimension, MLT to the power minus 2, and then unit of acceleration or any unit. Then you have in the Newton's law, force equals to mass into acceleration and statements like that. And then comes this R tends to 0, which gives you the singularities in Newton's law, Coulomb's law. You have Q tends to 0 for the test charge to be very small, for statements like that in the definition of electric field. And in derivative calculus, you obviously have this delta t tends to 0, like to define the velocity and etc. So of course you can see that these statements straight away symbolically does not hold any meaning. Why? Because on the left hand side you have physical dimension and on the right hand side you have just a number. So I don't know how to make meaning of this. If the symbols, is somebody questioning or okay? So certainly the foundations of physics are non-arithmetic in nature. So the question definitely comes that how to explain the arithmetic operations with symbols that do not represent numbers. Physical dimension is not number. Can this statement be both true and false? Well, Aristotle will say no. So a statement, an assertive statement cannot be both true and false. So this is where the logic comes in at the very basic, and you don't have to have a knowledge of the literature of logic to understand this. So now the problem is that something which is called the law of excluded middle, that this thing, that one assertive statement cannot be both true and false. If this is violated, then all of this classical logic fails. Classical logic, I mean, whatever you do in Boolean algebra also, like either 1 or 0, that kind of thing. So is physics logical? So that is the question. So if we look at this from the logician perspective again in the literature, in the history of logic, uh, and that you need to take my words for granted because I can't give you all the references here, but this is only one reference, this handbook of history of logic. You will find nowhere any discussion regarding this simple question. And more specifically, George Boole, who gave us the Boolean algebra, he said that to reason logically, uh, the first thing we need to assume is that any symbol and arbitrary mark must have a fixed interpretation throughout your reason. So the question is then, why is the logician silent? They don't ask the physicists this simple question, that how can you use some symbol which do not represent numbers as numbers? So is physics founded on a contradiction? Okay, so let's see. Uh, so here I have added at last a comment by Poincaré, and to all these young students who are right now listening to me to this talk, it is just a free advice to once in your lifetime read this book, Science and Hypothesis, which I have cited here. And it is probably the first line of that book, the very possibility of mathematical science seems an insoluble contradiction. It is a remark by Poincaré, and you will know who Poincaré is if you when you go to masters, and probably you already know by now if you have done special relativity thoroughly. So there are some necessary clarifications to be given. So what is the logic behind dimensional analysis? Of course, the definition of quantity and well, how we give the definition of quantity in terms of number and physical dimensions. The distinction between unit and unity or one, the number one. And for that, I have to clarify at first what do I mean by definition. Okay, so let me go to the meaning of definition. So before I go to the meaning of definition, I'll just coin a new term because you can see that the symbols which we call physical dimensions are used to express the physicality which we, I mean, the way we express physics. But we use it in as numbers also. So are those symbols physical or mathematical? So these symbols and all the expressions which I write, which involve these physical dimensions, these expressions I will be calling physico-mathematical. So mathematical expression means only with numbers, and physical means like with mass, length, and time, these sort of things. But when we use it for calculation, I will call it as physico-mathematical. So all the expressions of physics, if I write down, they are physico-mathematical expressions. Okay. So this is just a term, just to distinguish between pure mathematics and these expressions which we write down in physics. Okay. So what I call definition, an expression of a complex thought made in terms of elementary premises, which are elementary expressions, which are expressions of elementary thoughts, is what I call definition. Any definition is written in terms of physico-mathematical expressions along with necessary verbal expressions. So let us not go into those words. I have written these things down clearly for the logical people also, but it is better to give examples for what we mean by that. So when we define the derived physical dimensions, we consider as the elementary premises some physical dimensions, which we can't define but postulate. And it is like this mass dimension, length dimension, time dimension, etc. And from there, we define these things. Okay. So like the velocity dimension, which I have denoted by V, it is defined as LT inverse. And same for the acceleration dimensions, force dimension, and so on. So what is the role of the verbal expressions? The thing is that I showed the examples which were the simplest. So that's why I didn't need the verbal expressions. But now look at Maxwell's definition of electric field. So this is an excerpt from Maxwell's book, page number 45, a treatise on electricity and magnetism. Now you see, this all of these words, it is converted into only one equation, F equals to RE, where F is the force, R is denoting here the electric field, and E is some charge. So is this conversion of these all these verbal words into this single mathematical simple expression, a physico-mathematical expression, is it justified? Well, this is what we are going to investigate here. I will come back to this later, but before that, I need to clarify a few more things. So, let's make a comparison of this concept of definition with what physicists say. So, in physics, if you ask a physicist, the general view is that the definition for physics or for the physicist is operational. What is meant by that? Well, this P.W. Bridgman, Percy Bridgman, he was a Nobel laureate during 1920s, 30s. So he brought in the main concept of, well, he popularized the concept of this operationalism. And for him, the definition of a concept is synonymous to the corresponding set of operations. Like when you do experiment, whatever you do with those experimental apparatus, like do the measurements, that will define the concept you want to define. Okay. But there is a problem with this. What is that? So there is a profound gap between this experience. By experience, I mean what you are experiencing by doing the operations and what you express. For example, put a dot with a pencil on a paper and call it zero extension. This is the usual explanation of the expression R equals to zero. For example, in Newton's law of gravitation or Coulomb's law. But you can see that if you put a dot on a paper, you are certainly seeing an extension, because without that extension, you can't see that dot. So there is a clear contradiction. So there is a gap between the experience and expression, and we don't take into account. We don't take this into account. And of course, you might be thinking about, so what about the geometric representation of real number system? Well, this is a quote from René Descartes, the Cartesian system created. So he refused to write exactly. So taking one line, which I shall call unity, to relate it as closely as possible to numbers. So you can see that he hesitated. But for the modern physicist, there is no problem. He just carries on. So this is what I have quoted at last. It is a quote from Roger Penrose's paper. The body contracts and continues to contract until a physical singularity is encountered at r equals to 0. Well, you all know this was the Nobel Prize-winning paper, awarded in 2020. So let me now go into the discussion regarding quantity, physical dimension, and number. And this will, justify why I am nitpicking with these definitions and these sort of things. So here is the definition of quantity. So the main thing is the second line, that if I consider a quantity of charge denoted by Qi, then I define this quantity in terms of symbols like this, where NQi represents a complex of thought, where N stands for the concept of number, Qi denotes which quantity this number is representing, and this Q is the physical dimension, denoting the physical dimension which this quantity carries. And of course, it comes with a condition that NQi must be greater than 0. So it is not equals to 0, and I'll be only considering positive numbers for simplicity. Okay. So this definition goes for all type of quantities like mass, length, time, and etc. So this is just a statement of the definition, but you have all operated with this earlier. But that definition was not stated in the literature of physics. So here is the clarification of why I put that condition that NQ should be greater than 0, because I just avoided a conflict. So when I define the quantity, I am assuming that it exists. But if you put NQ equals to 0, it will give you an impression that it conflicts with the premise because it is non-existent. So therefore, this zero quantity is a meaningless statement. And this is somewhat akin to what has been earlier discussed in Buddhist reasoning, but most of you will not know this. But this is a quote from one famous logician of the West, which we all follow, that for up to now, no one has ever seen or touched zero pebbles. That is, zero quantity is a meaningless statement. But of course, we write physics like that. So there are some further clarifications which we will need as we go ahead. And this is what happens when we compare two charges. So this comparison is written like this, where Q2 equal to N21 Q1, where Q2 and Q1 are just two charges. This all you know, I'm just defining it properly in terms of symbols. But this N21 equals to the ratio of N2 and N1. This is just a number. Okay. So when we say that Q2 is greater than Q1, then it means actually that the number N21 is greater than 1. And you can just go on like this with the mathematical symbols. This is just a clarification from the definition of quantity. Okay. So here is one further clarification which I could not avoid, that if NQI would have been equals to 0 would have been allowed, then we run into a trouble, because we could have actually written that Q2 equals to 0 Q1. Now this has no corresponding verbal expression. Even if you want to or try to write some expression, it will be grammatically incorrect. For example, I have constructed one wrong example here in English. Q2 does not exist or vanishes compared to Q1. You can see that this is wrong. But I'm saying that if you try to explain this Q2 equals to 0 Q1 in terms of English, what happens? These are philosophical and logical problems which have been encountered earlier also. For example, one famous philosopher, George Berkeley, uh, called the evanescent quantities, an adjective which was used by Newton while writing calculus, that those, or may we not call them the ghosts of departed quantities. So the problem is there. Now come to the logic of physical dimension. So what is the logic of using this physical dimension? And what do I mean by the middle way? So when we define the quantity, certainly physical dimension is a distinct, I used physical dimension as a distinct concept from the number. So there, why I considered it as a not number is that if you write q plus q, that does not represent counting. Like in arithmetic, we write 1 plus 1 equals to 2. And similarly, if you go for the multiplication, like 2 into 2 equals to 4, 2 into 3 equals to 6, there is a meaning in arithmetic, but in physics or in for this physical dimension, these symbols don't have any meaning in terms of multiplication, like q into q, m into l, and like that. So that's why I said that physical dimension does not represent number. But again, when you write that sum of two charges, sum of two masses, like that, addition of quantities, then you certainly treat this capital Q as a number, because you take it common, like a non-zero number, and write it like this. Okay. So this was the reason why we were debating regarding the status of what Q is. So now, so then what is the reasoning behind writing terms like this? So here, if you see this kind of writing, to write this expression q1 into q2 equals to nq1q into nq2q, and then writing it as a q square dimension, you need to make a postulate. This is beyond arithmetic. This is not in the arithmetic. This is something you need to postulate by hand. Otherwise, these sort of writings don't have any meaning. Fine. So if this discussion, if you write down in a single structure, then you see that once you are using to define the quantity q as not number, but when you are adding to quantities, you are using q as number. So when you write q equals to q1 plus q2, for these individual definitions, you need to hold the statement that q is not number, but on the whole, for this operation, you have to have the negation of that statement. That is, q is number. This is akin to Buddhist logic, which was championed by Nagarjuna, and this is something which was called middle way or Chatuskoti in Sanskrit. But I couldn't find the original writing of this spelling of Chatuskoti, so I wrote it in English. And so now I have clarified what do I mean by middle way. Now let us come to unit and unity. So what is the difference? Here you all know that unit is a chosen standard quantity with which you measure in multiples the other quantities, and it carries a physical dimension. Sorry, and unit is the numeral. And why I am emphasizing this difference? Because you will often see in the literature of mathematics and physics also that people write the number 1 and then call it a unit. This is a general practice which you can go through the literature and verify. So that's why I just revisited this and clarified this. Okay. Now, after defining the units, what do we mean by measurement? That whenever we measure a quantity in terms of the unit, we get some whole number, which is the general rule, I should say, which we consider. But what we don't consider here is that since we are telling between the experience and our expressions, that on practical grounds, we must consider an error here. Because there is always something left over when we do measurements. If you go, for example, to the lab and make measurements, you will understand that you need some scale to measure something, and there are some marks which have thicknesses. You cannot remove those thicknesses of the marks. If you remove those, then measurement is not possible. But if you have those marks, then those are the irremovable errors which you have to consider. Otherwise, measurement will not be possible. But at the same time, the error will be there. But this is not the scenario which the theorist accepts. The theorist writes those epsilon as 0 and consider it as a whole number while writing down the expressions. So this is a quote from Einstein, that here we have assumed that there is nothing left over. And this difficulty is got over by the use of divided measuring rods. Well, this was an assumption by Einstein while he was explaining the logic of writing special relativity. His arguments contain this. But then the experimentalist should ask that, can you see a crosswire without thickness? It is just like the simple example which I just gave, the marks of your scale. And also, if you divide a rod again and again indefinitely, does it remain useful? No, I think no. And this is what the experimentalists believe. For example, this is a quote from Bridgman, the Nobel laureate who I quoted earlier also, that all results of measurements are only approximate. That such is true is evident after the most superficial examination of any measuring process, like the examples which I gave just to you. And such view was shared by another Nobel laureate, Arthur Eddington, who actually took general relativity correct. This is just fact. You don't need to know the theory. So now with all these experiences and all these discussions regarding the experience and expressions, like how we express logically in physics, let us go to the definition of electric field. So here is the textbook definition of electric field. I have not gone into the explicit details, but this is a shorthand notation. So we begin with the Coulomb's law, that force between the two charges and blah, blah, blah. And then in the electric field due to Q2, which I consider as source charge, we define it like this with this symbol. So this EQ2 is the electric field due to charge Q2, which is defined like this, where this limit Q1 tends to 0 is extremely important. This Q1 is called as a test charge. So what we will be discussing here is that what are the possible interpretations of putting this limit. and how well reasoned is that. So let me come to the first explanation, and so that there is a circular kind of reasoning that goes on. So one explanation goes like this from the physicist. The statement limit q1 tends to 0 is used to signify that the field due to the test charge q1 must not distort the field due to q2 or must not affect the body with charge q2. So now, to affect Q2, Q1 must produce an electric field because the 2 point charges are at distance. So you are conceiving the thought of electric field with this statement, that the affection. So here the actual assumption is that this Q1 tends to 0. This is actually equivalent to EQ1 tends to 0. That is, the field produced due to Q1, the test charge, is negligible or vanishing, whatever. Or more explicitly, this EQ2 should have been defined like this, that limit EQ1 tends to 0, F by Q1 equals to KQ2 by R squared. So therefore, you can see that to define EQ2 or the electric field due to the source charge, the definition of electric field due to Q1, that is EQ1, is explicitly presumed or assumed. So this is a circular reasoning and considered fallacious by the logicians. Okay. So here the physicist may object like this. And what is the objection? The physicist's objection goes like this, that EQ2 is defined on the basis of a presumption of EQ1. That is fine. But now see that the Q2 is not equals to Q1. So the circular reasoning is not exact. The circle is not exact. And therefore the fallacy is not obvious because those two are not the exact concept. So then the logician replies now is that Q1 stands for some charge and not electric field due to some charge. The explanation must not involve the words electric field, the same thing which I was telling. Therefore, the fallacy is the immorality of the expression. That is, use the words electric field to explain Q1 tends to 0. Fine. So you have to express correctly what you were trying to say verbally, and then how are you converting it to physico-mathematical expressions. And then there is also an alternative explanation which goes on, or one can give, is that Q1 is extremely small compared to Q2. Okay, for this limit Q1 tends to 0. In this way, one does not need to presume EQ1 to define EQ2. So you avoid mentioning the word electric field. However, this is again immoral, like the one I said earlier, that limit Q1 tends to 0 does not contain any reference to Q2. Well, this is not the involvement of the electric field, but the thing is that limit Q1 tends to 0 is only referring to one charge Q1. But how can you then state this comparative expression? Okay, so the correct physico-mathematical expression corresponding to this verbal expression which I have written in quotes, that Q1 extremely small compared to Q2, should be like this, that Q1 very less than Q2, or equivalently, if you want to write it in terms of equality, Q1 equals to some epsilon number, epsilon 1 to Q2, such that this epsilon 1 2 lies between 0 and 1, and actually very less than 1. Okay, this is simple conversion between your verbal expressions and physical mathematical expressions. Okay, so then why this reasoning is incomplete? Because there are some subtle questions which come up if you try to adopt this sort of reasoning. It is because if you assume Q1 very less than Q2 to define EQ2, that is source charge, then there should be some Q0 which is very less than Q1 that you need to assume to define the field due to charge Q1, that is EQ1. And similarly, you can proceed like that for all charges. Okay, because EQ should be definable for any Q. So the question now comes that is there a smallest charge, say QU, that can be used as the test charge to define the field due to any source charge with, yeah. source charge designated by QS, which is very greater than Q, or the other way around? The answer is yes. Why? Because you all have studied in your school and then in your college this famous oil drop experiment by Millikan and Fletcher. Well, you probably know it as Millikan's oil drop experiment, but Fletcher was his PhD student and he had a very big contribution in that. That has come up in very recently in the 1980s. Okay, so then this uh, needs clarifications. So the problem of the smallest charge assumption is that, or not an assumption, but that answer, yes, is that the Coulomb's law has no restriction on the charge we use. Okay, so the QU, which we consider as the smallest charge, that should obey the law. So QU must exert the force on the source charge, which we have used as the test charge. But how? It must create a field. Okay, so that I have called EQU. To define EQU now, there should be a necessary assumption that there is a smaller charge which you should be able to use as a test charge, say Q naught less than QU. But once you assume this, then your violation of considering QU as your smallest charge gets into trouble. So how to resolve this dilemma? So we will be going to resolve this dilemma a bit later. But before that, let me convince you that the kind of problems which I discussed with you are actually uh, present in Maxwell's definition and Jackson's definition, as I promised at the very beginning. So here is a relevant excerpt. I don't think you will be willing to reading all this. So trust me that I have copied it correctly into the next slide. So if you take your time after this talk to go through that definition of electric field, you will see that there is the first part, there are two lines in the beginning which gets into the problem of circular reasoning that I have discussed. This is about the Maxwell's definition. And now I will point out one by one the highlighted texts. I will go back again one slide. So you will see these colored texts which I have shown here. If the body is very small, then its charge also very small. This I will highlight and analyze that how can we make it correct, because these are problematic. So if the body is very small, this is an incomplete statement because it is not stated that with respect to which body, which quantitative mass or volume or density or what. So I will assume that it is mass, and then the corresponding physico-mathematical expression should be like this, where this small m, this is the mass of the test charge, and this is some mass unit probably, which we can assume because we all fix our standards while doing measurements. So there should be some expression like this. Similar statements go for this. Its charge also very small. So this is also an incomplete statement because it does not state with respect to which charge. So a completion takes a physico-mathematical expression like this. And you have to consider another epsilon number, epsilon q, which I have denoted here, which is very less than 1, but positive. Again, there was a part of the phrase not to be sensibly disturbed. So what do we mean by sensation? When we touch something, we feel some force. Also, we apply force. So the concept of force arises. And okay, so if force F naught is responsible for sensation, then the force causing the disturbance F should be very small compared to F naught. And this should be written in terms of a physico-mathematical expression like this, where you introduce another epsilon number, epsilon f. It has to be done, otherwise there is no choice. And finally, there is the statement E is very small. Again, you introduce another epsilon number, epsilon. So that's why I told you that the single expression F equals to RE, which I mentioned very early, that was not adequate to explain all this. And this one needs a special mention that there is a misunderstanding between unit and unity, because Maxwell mentioned charge E could be made equal to unity. But you can see E is some quantity of charge, but unity is the number one. Okay. So symbolically, it should be looking like E equals to 1, and then you are in trouble because there is physical dimension mismatch. So what is the meaningful alternative to E equals to 1? Simple, that choose E to be equal to some unit. That's it. So this looks like this expression that E equals to C, where we can introduce some epsilon E, but it is equals to 1. Okay, because there is an equality between E and C. But if you do this, then Maxwell is in trouble, because a Maxwell statement needed E very less than C, and this becomes false. And this you can see by going back to the fifth point in the previous slide, which I don't want to waste time into going into there. So the concept of field is not definable in the way Maxwell did if we actually convert the verbal expressions into physico-mathematical ones. Okay. Now come to the comments on Jackson's definition, because this is a much modern book and you want to see what happens to this. So this one I want to read. Okay, so the electric field can be defined as the force per unit charge acting at a given point. One must be careful in its definition. However, it is not necessarily the force that one would observe by placing 1 unit of charge on a pitch ball and placing it in position. The reason is that 1 unit of charge may be so large that its presence alters appreciably the field configuration of the array. Consequently, one must use a limiting process whereby the ratio of the force on the small test body to the charge on it is measured for smaller and smaller amounts of charge. Experimentally, this ratio and direction of the force will become constant as the amount of test charge is made smaller and smaller. So you can already sense similar problematic statements by Jackson. So here are those highlights. 1 unit of charge. So this is again incomplete because there is no comparative statements. Then, there comes the limiting process. So what does come into mind when we hear about a limiting process? It's some sort of an infinite series, but in electric fields definition, we don't see that kind of expressions. So then Jackson mentioned the small test body, and again, this is an incomplete statement, and we can complete it in the same way as we did in case of Maxwell. That is M less than capital. And then smaller and smaller amounts of charge, test charge is made smaller and smaller. Jackson did not mention any sort of comparative quantities, and with what respect to what quantity is he comparing? So the question comes that does smallness has a limit? So now what happens if we go to explain the verbal expressions which are involved in this limiting process? So we focus on a particular part of Jackson's definition, which you can read later, but I will show you only the part of the physico-mathematical expressions, that how it looks like if you turn it into this kind of symbols, the physico-mathematical symbols. So at first, fix some charge unit C, mass unit capital M, acceleration unit A naught, and which of course will give a fixed force unit F naught, which is defined like capital M written with A naught. Okay. So this we fix at first because we need some standard for comparison. Then assume that the small test body means small mass, as I have mentioned earlier. So you have some epsilon number here, which lies between 0 and 1. Then force felt by the test charge, which you express it by using Newton's law, F equals to ma, and in place of m and a, you put these expressions, that epsilon m capital M and epsilon a naught. Okay, so of course here I have not mentioned one thing, that this capital A is the acceleration which has the relation with this acceleration unit through some number epsilon a. Okay. So
of
this
the
epsilon
academic
A, I
year.
have not said that it is less than 1 because there was no mention of this, what the acceleration is in Jackson's definition. Okay. So let us consider this epsilon A hanging here without any condition. So here I have defined what epsilon F is, you can see in this expression. So these are just the conversions of the verbal expressions into physico-mathematical ones. And finally, if you see that if you want to define the electric field, it somehow looks like this, somewhat looks like this. That this limit, if you turn it in terms of the quantity, it is q very, very smaller than c, which I have written epsilon q very, very less than 1 or tending to 0. You can write that also. So the epsilon e is some number which is actually the numerical representation of what we mean by the electric field. So it can be discussed as follows in the last line, that E by E naught, where E naught I have defined here, that F naught by C, that is the ratio of the units. This epsilon E is now written like this. Okay, where epsilon m is less than 1. Now, what does this epsilons mean now? I mean, what we can do with this? So if we consider some fixed epsilon less than 1 and choose epsilon q smaller and smaller compared to unity, which actually Maxwell mentioned in his definition, then you can see that for epsilon e to tend to a constant value, say phi naught, epsilon a must have the general form of this. So this you can consider as an ansatz, because this is what you need to post. I mean, as an ansatz to express the the verbal expressions into as a physico-mathematical ones. Here the bn's are some numbers fixed by the choice of epsilon m, which we have fixed in the first line. Okay. Now choose epsilon q extremely small compared to unity, but not 0, because you cannot put exactly 0. This leads to the following approximation, that these answers leads you to an approximate result phi naught by epsilon m. But remember, I have used an approximate sign because this is not an exact result and you actually are handling an infinite series here. Okay, which you can't know because it's infinite. But this is a satisfactory result which can be used for practical purpose. This is similar to when we do a square root of 2 or square root of 3. We have an infinite continued fraction representation, but we truncate somewhere up to which we need. It is just similar to that. But to make this choice of epsilon q, you need some postulate, because you need to clarify some sort of statement like this, that whatever quantity of charge I may choose, there always exists a smaller charge in theory. This you have to postulate, because there is nothing like this in physics as far as I know. So here is the necessary postulate, and I will explain the word undecidable here. So the postulate goes like this, that considering a quantity of charge written in terms of symbols to formulate a theory of physics, for any charge denoted by q, there always exists some charge q prime such that q prime less than q, or equivalently, you can write it in terms of this epsilon number. So by this postulate, then you can consider the limiting process to be valid. But when experiment yields the smallest detectable charge, then by the above postulate, the theoretical definition of the electric field is still possible. There is no logical conflict. Okay, so why I have said this no logical conflict? Because in the experimental paper where Millikan reported the detection of the electrons, he used the definition of electric field there also. So if the detection of a smallest charge would have falsified the definition of electric field, then that paper was actually falsification of a theory and not the verification of a new result. So without this postulate, there would have been a logical conflict, which nonetheless have never been considered by the physicist. Now there is an added clarification here. The theoretical existence of charges q by the postulate these QUs are only smaller than E. What is that E? The experimentally detectable charge, the smallest charge or the electron, which you know. So these QUs I call as undecidable charges. But why? This name, I'll explain this term undecidable now. So as I told you already, these are experimentally undecidable. What do I mean by that? Is that these QUs cannot be detected. And therefore, because you have already detected the smallest charge E, which is greater than Q. So the thing is that if you can't detect something, you cannot verify its existence. I mean, these QUs, which are less than E, these can neither be experimentally proven to be true, nor can be experimentally proven to be false. That you cannot say that QU does not exist. But also you cannot say QU exists by experiment. That means you can't experimentally detect this. But what about theory? Can you theoretically prove it to be true or false? No. Why? Because of this explanation. So consider this postulate as a hypothesis. So hypothesis is different from postulate in the sense that postulate is something based on which we build a theory. For example, Einstein's postulates of special theory. Okay, so considering that, you build a theory upon this. But hypothesis is something like you have in mathematics Riemann's hypothesis, and there are other hypotheses also. You either can prove this or you can also falsify. If it is a theoretical hypothesis, then you can do it in theory. Okay, what you can prove or falsify, it is called hypothesis. But it is not like that. Why? Because if you hypothesize these QUs and then say that, okay, so theoretically it exists, if you give a proof of that, it becomes a logical tautology. And what is that? You assume it to be true and then you build a theory on that truth and arrive at that same truth. So this is a tautology. And the other, it goes other way around, that if you falsify this postulate within the theory, sorry, the hypothesis within the theory, then you are saying that, okay, QU cannot exist if I assume its existence. So it leads to a contradiction. So that is why I have called it as a postulate of undecidable charges and not hypothesis. Okay, so this was so for the electric field. Now I'm going to conclude this. And why uncertainty? Because this is part of my future work, which is based on what I've discussed here. And that's why it's uncertain, because I have not completely written it down. But there can be another meaning of the word uncertainty here. And what is that? So you must be thinking that since I've been talking about this infinitesimally small and these sort of things and quantities, so what about the definition of derivative? So this is a quote from Cauchy. Okay. So if you go to the book which I have mentioned here, it's a very recent English translation of Cauchy's book. You will see that while Cauchy defined the derivative, which you call like dy dx, where y is a function of x, he said that while considering this ratio delta y and delta x, the two terms indefinitely and simultaneously will approach the limit of zero. Okay. Here I have ignored his incomplete statements like this infinitely small with respect to what and this. But what is important here and interesting as well is that if we convert these to physico-mathematical expressions, considering these as quantities, which Cauchy also said, we should not write it as dy dx defined as limit delta x tends to 0 delta y by delta x. We actually need to write that limit delta y tends to 0 delta x tends to 0 delta y by delta x. Okay, it is just the conversion of the words which Cauchy said. Okay, now here comes the example of the definition of instantaneous velocity, because this is the first example of the application of derivative which we consider in physics. So let us fix some standard of length and time, lambda naught and t naught, and then write delta x as some number delta nx lambda naught, and as well as for delta t, introduce some number delta nt and t naught, and then the limits, we consider the limits as this delta nx tending to 0, delta nt tends to 0. So now you have a meaningful explanation of this infinitesimally small and compared to the comparative statements which I am saying. So this limit delta nx tends to 0, this is equivalent to delta x very very less than lambda naught, and then for delta nt also, as it tends to 0, this is equivalent to delta t very very less than t naught. Okay. So now according to Cauchy, the instantaneous velocity should be defined like this. Fine. This limit delta nx tends to 0, delta nt tends to 0, and here we write it like some nv v naught, where you define v naught as lambda naught by t naught and nv as this thing in the parenthesis. Okay. So this is just the definition. The same thing goes for instantaneous acceleration as well. Here you consider some number delta nv and define delta v, the change of velocity, as like delta v equals to delta nv v naught, and you denote the limits as this, that there is a very very less than condition which is equivalent to the limit. So then your definition of instantaneous acceleration goes like this, where you again have two conditions and you arrive at some expression like a equals to na a naught, where na is defined as the term in the parenthesis. Similarly, you can do for the rate of change of momentum, because you need that for Newton's laws. And here you can see that you need the condition, one of the conditions as delta p very very less than p naught. There is a condition there. Fine. Now, so here is a derived condition which you can write. For instantaneous velocity, you wrote that delta x very very less than lambda naught. Then to define the instantaneous rate of change of momentum, you wrote this delta p very very less than p naught. From here you can write down the product of these two quantities as delta x delta p very very less than L naught, where L naught is of angular momentum dimension, if you can say, or momentum dimension into length dimension. So now you can see that if this condition is violated, then Newton's laws will not work, because all those definitions of, in calculus of these quantities, they are not possible. But this condition, which goes like this, looks very familiar, right? So this is where I'll stop, and I believe you can sense some similarity with something like Heisenberg, and you have read Heisenberg's law.
Is it Heisenberg's uncertainty principle, if I'm not wrong?
Okay, so this is a big statement to make, because this was just a three-liner. Okay, so that's why I said Heisenberg is laughing, and you will also laugh at me if I say that this is Heisenberg's uncertainty principle. And I need a lot of work to do to say this, because we know h bar, or the reduced Planck constant or Planck's constant, as something is fundamental constant. Okay, so to claim it as the the Planck's constant, this L naught, and as well to claim it as Heisenberg's uncertainty principle, I need to explain what do I mean by fundamental constant. The problem becomes philosophical. Why? Because I need to reconstruct theoretical physics, or at least the basic physics, from the scratch with these sort of epsilon numbers and whatever analysis I have showed to you. And then I should arrive at this. And then if you see the statements which I have explained here, or the kind of things which I have said here, the notion of fundamental truth or ultimate reality or fundamental reality which is at the foundation of most of the research which is done in theoretical frontier, like quantum gravity and these sort of things, they consider this h bar as sacrosanct. Okay, so this cannot be violated. But here, I don't have the concept of ultimate reality. It's only relation. You assume something hypothetically, and then you do some experiment and fix your limitation until you can go. You just test with your apparatuses and etc. Okay, and below that, it's like the undecidable charges that you can't do anything about that, but you just assume and write down the theory. So the reality of this materialistic approach which we have in physics, this is relational for me. Okay, I could not go with those sort of philosophical jugglings here. I wanted to keep this extremely simple, and because I have a audience of from physics background, I believe, but that is what I have to say. I can't claim that this is Planck's constant, because Planck constant is Planck constant, which Planck gave. Okay, that is also fixed by experiment, that I know. And this L naught is also a statement about experiment. Why? Because we are choosing the lambda naught and p naught, and these are the units of measurement. And these can be chosen. These how can we choose this? Until we are able, we can divide the rod, divide the rod until it becomes useless. Okay, so I am not going to claim that this is what do you say, Heisenberg uncertainty principle, because I am not doing quantum mechanics. I am just stating what the experimentalists had to say in a meaningful language with which we can do mathematics, the physico-mathematical expressions. That's it. Nothing more than that. I'm not here to claim anything. I'm just here to discuss with you guys. Probably mostly students. I can't see anybody. So yeah. So that's my answer. Any questions? Well, thank you.
Okay, thank you, sir.